All right, so last example of 8.4. Like we were just saying, example 5, the power in the numerator. You've got 3x to the fourth plus 1 is higher than x squared minus 1's degree. The highest power up on top is bigger than the one down below. What do we have to do? We have to break this down by long division. So tell you what, I'm going to scroll up a little bit, just so we've got some space. Remember, every power of x must get represented. Some teachers call these the ox terms. And that can sound so funny. Why do we call it an ox? Well, you can see like the 0x looks like the word ox. But you don't want to have the very uncomfortable situation of not having like terms lined up. That gets so confusing for kids. If you put your placeholders in, you'll avoid that. Now, it's been a while since we've had some long division of this complexity, perhaps. So let's review it. Always a good thing to review a little bit. Long division, you always look outside. Your highest power is x squared. Inside here, you've got 3x to the fourth. What would I multiply to x squared to get 3x to the fourth? 3x squared. Notice I'm writing 3x squared above the x squared inside the division to just line up all my like terms. I like to do that. I think it can help. Just keep everything organized. 3x squared gets multiplied to x squared. That's 3x to the fourth. 3x squared times 0 is just a 0. That's 0x cubed. 3x squared times minus 1. That's a minus 3x squared. But what do we always do after we've multiplied through? We subtract. Subtracting, we know in algebra, is really adding the opposite. That's what it means to subtract. It means to add the opposite term. So just change all those signs. I've detailed that in red. You're going to see quickly, I hope, that 2 columns cancel out. We'll have 3x squared right here. Because 2 terms canceled out, bring down 2 more terms. The number of columns canceled out will require how many new terms are brought down. And now we repeat this process. We can say, well, what times x squared would get us a 3x squared? I hope quickly we can say the answer is 3. We can multiply 3 to all 3 of these. Get 3x squared plus 0x minus a 3. Of course, right now we're going to subtract. This cancels out. And then these 2 columns have canceled, just leaving you with a 4. There's nothing left to bring down. That's your remainder. Back in 3rd grade, you would have written that big R4, right, for a remainder of 4. But shortly thereafter, you'd say, well, look, I'm going to say 4 all over the divisor, what is outside here, what we're dividing by. So that becomes a plus 4 over x squared minus 1. Okay? That's your new integral. That's your new integral. And I think what is going to become quickly apparent is that we still have an algebraic fraction that's right here. So the big question is, because I don't recognize an obvious antiderivative, by the way, if it would have been x squared plus 1, that's something we could do, isn't it? That antiderivative would be an inverse tangent, which would be great. But because I look at that and I'll say, well, I don't know a nice simple antiderivative. Really, what I'm wondering is, could we maybe break that down with a partial fraction? X squared minus 1 will factor. It will factor into what? X plus 1. X minus 1. Now, on the front page, we dealt with that uncomfortable situation where you had repeated factors, like with prime factorization, we dealt with that 5/8 and 8 was 2 to the third. In example 2, we factored out x squared. We had x to the second power. Do we have any factors down below to the second power or the third power or any higher powers? No. Everything's raised to the first power. And that's what you want to see. You don't have to do the repeated factors. So instead, we can jump quickly to just saying this is a over x plus 1 and b all over x minus 1. And now we can, just continue to break this down. I hope we're getting more comfortable with a way to break this all down. If I multiply through by the least common denominator, what would my left side be? A 4. How about the a over x plus 1? When I multiply that by the LCD, what would I have? A times x minus 1. My x plus 1 would cancel out. And then my last term would just be what? B times x plus 1. I would get the x minus 1s to cancel out. And right now, do you think we should do coefficient analysis? Should I distribute everything out? Or should I just substitute in some friendly values of x? Yeah, let's substitute, right? That's the easier way to do it. If we're really on our toes, if we're really smart, we could say, hey, you know what? Let's let x equal a number. What should we let x equal? A 1, you know it. Left side's a 4. 1 minus 1 is 0. 0 times a goes away. 1 plus 1 is a 2, so we'd get 2b. But wait a minute, that means b is really what number? A 2. Look at that. What else could I let x equal? Yes. So the left side's a 4. Negative 1 minus 1 is negative 2. We'd get negative 2a. And this b expression would completely cancel. So what's a going to equal here? Negative 2. Now, guys, if you're really, really, really on your toes, you should be quite happy because you can say, wow, now I have two separate fractions with these values right here that I can put into play, that I can get some help with. The original integral now, and I'm just recopying example 5. It's going to be 3x squared plus 3. That's what our long division showed us. But that fraction up here in green is really a over x plus 1. My a is negative 2 over x plus 1. Then I'm going to have over here is my b over x minus 1. My b is a 2. And guys, right now, if you look at every part of that integral, well, all 4 separate terms there, I can find an antiderivative for all of them. Okay, let's finish the problem. What's the antiderivative of 3x squared? That's plain and simply x to the third. How about the antiderivative of 3? 3x. Ooh, what's the antiderivative of a negative 2 over x plus 1? Negative 2 ln of x plus 1. One more antiderivative, that's going to be a plus 2 ln of x minus 1. Put in a plus c, and you are done.